Okay, I'm just going to give you a bit of recap on perpendicular distance since you haven't done this since at some point in GCSE. So here's a GCSE question um, where you've got a 300 Newton force on a pedal in 3 different positions, and the question is which position does the force have the greatest turning effect? Um, in order to answer it, you need to know the perpendicular distance in each case, since moment equals force times perpendicular distance. So, if you've forgotten it from GCSE, I'll show you the technique that I use for my GCSE students. So, step 1, extend the line of action of the force. So, go along the force, the line of the force, and extend it in both directions with the dotted line. There's the line of action of the force. Then you want to draw a line from the pivot to the line of action so that it meets it at right angles. So if I go from the pivot here to the line of action, okay, I want that line that I've just drawn to meet the line of action at right angles. Now this one has not met it at right angles, so that is not the perpendicular distance. Okay, let's get rid of that. This line here does meet it at right angles. That is the perpendicular distance. So this would be the perpendicular distance D, goes from the pivot to the line of action of the force and meets it at right angles. In this situation, the line of action goes right through the pivot, so the perpendicular distance is just 0. And in this case, I'll go from the pivot to the line of action of the force and meet it at 90 degrees. That's my perpendicular distance D. Now, this is A-level, so you need to be able to go a bit further and not only identify where D is, but calculate what it is. For us, this is pretty simple. In all 3 cases, it turns out. In C, we know what D is because they tell us it's 16 centimeters. In B, we know what D is because we just worked out it's 0. But in A, we're not immediately sure what D is, so we've got to use some other technique to calculate it. Now, if I just redraw it over here, we've got our D here. We do know from another diagram that the length of the crank arm is 16 centimeters, and they've told us that this distance here is 14 centimeters. Now that distance is not the perpendicular distance, but it's useful for us because we've then got a right angled triangle with D 16 centimeters and 14 centimeters, and you would be expected at A-level certainly to be able to deduce D from that using Pythagoras. You might want to check that now and calculate what you think D is, that you would then put into your 300 newtons times D to get your moment. I think I did it a minute ago and it was 7.7 centimeters the perpendicular distance, but check that. You might also have situations where you're not told one of the sides, but you can work out one of the angles, or you're told one of the angles. In that case, you'd be expected to use trigonometry to work out the perpendicular distance. So the key skill is to identify what the perpendicular distance is and then find a way of calculating it. I'll just show you another technique that I use sometimes just because I think it just looks a bit clearer to me and a bit easier. You can use whichever technique you like in different situations. So here we've got a beam that's attached to a pivot here, so it can pivot up and down. It's being supported by a force over here from a rope or something. The question is, what is the moment of that force about the pivot? Well, you could do it the way I've just showed you. Extend the line of action of the force. Draw a line that goes from the pivot to the line of action and meets it at right angles. Call it D. The moment is then the force, 115 newtons, times the perpendicular distance D. All you've got to do is work out what D is, and you might be able to look at the diagram and perhaps work out what one of these angles is here, call it theta, and then do some trigonometry to work out what D is, and there you are, you'd have the answer. The way I sometimes do it, just to give you an alternative approach, is to do some components. What I might do is resolve this force into 2 components at right angles to each other, because makes my life a bit easier, and I think it sometimes just gives you a neater diagram. Now if I resolve that into two components, this component, if we call them A and B, component B, the line of action of that component goes straight through the pivot. So there's no perpendicular distance, there is no moment from B, component B. Component A does have a turning effect, there is a moment about the pivot, and the perpendicular distance between component A in the pivot is that distance which they've told us. Okay, so the moment is A times 0.55 meters. So to work out what A is, all we have to do is resolve the 115 Newton force to find component A, and in this case it would be 115 cos 30 degrees would give us A, times 0.55 meters would give us the moment, and there you can work out what the moment is. Interestingly, the expression you get is identical whichever way you do it. Okay, so mathematically these two techniques are equivalent. This thing here that you get from resolving the component and timesing it by the distance is exactly the same as if you had somehow deduced what d is and multiplied that by the 115 newtons. So mathematically it's equivalent, it's just a different way of visualizing it and a slightly different way of thinking about it, and you can use whichever technique you like in different situations as long as you get the right answer. So I hope that's useful to recap something from GCSE, and we'll give it a bit of practice next lesson.